Welcome to the VEX Isn't Scary project. This is part 1 and we're beginning on our setup. So with all of the knowledge that we've gathered in the first half of this series, we should have a decent starting point to begin on an interesting VEX-based project. So what exactly are we going to create? Well, we're going to be creating this effect. And to understand what goes into this, let's do a quick breakdown. So the idea is we have this line, and we have a point on that line that goes back and forth along the line. Now, as you can see with this arrow, when the arrow touches the end of the line, the point meets it. And if we introduce another line that follows those same rules, we end up with this. And we can keep adding lines and points, and we end up with this. And eventually, we have what looks like a circle. Now, if you can't really see this effect, let's add more lines. And now you can probably see the optical illusion that we're going for. This is because of simple harmonic motion, which we can achieve with sine and cosine functions. In fact, sine and cosine are the backbone of circular motion. I'm no mathematician, and so I won't act like I completely understand this. However, there is a great video from Numberphile over on YouTube called Beautiful Trigonometry about this exact concept if you'd like to learn more. Now, let's break this down. The easiest part of this effect would be to create the lines that the points follow. Basically, we want to evenly cut a circle with lines running through the center of the circle. Now, if we wanted to cut the circle, we can either think of each line as a single line or as 2 points on opposite sides of the circle. The only tricky part is evenly cutting the circle. If we have 2 lines and 1/3, we don't want to add another line like this. We would want to adjust the existing lines like this. In other words, we want our points evenly spaced around the circle. Now that may sound a bit confusing, but when we get into this, it'll start to make more sense. Alright, so in Houdini, we can go ahead and drop down a geometry node. We can call this VEX project and then dive inside. We're going to drop down an attribute wrangle, just like that. Now, we don't have anything to start with, so we want to run over detail. So remember, if you have points, you run over points. If you have primitives, you run over primitives. If you don't have anything, in our case, then you want to run detail. So it will just run independent of geometry. Alt plus E to bring up our VEX expression editor. Cool. So what we're going to do first is what we usually do, which is variable initialization. A variable that can track how many lines we want in our circle, which also means how many points we have. So let's create int lines, and we can make it equal to a channel integer, and we'll just call that channel integer lines. So that'll give us a slider where we can control how many lines we want. Next, we want a float x and a float y. What we're going to be doing with that is defining where on our circle this point needs to be added. So we can create a float x, and we can just put comma y, and make them both equal to 0. So this is a great way to initialize 2 variables on one line if you know that they're both going to be the same data type and the same value. So x and y, both floats on the same line. Cool. We also need 2 vectors. We need a vector which holds our start position for our line and our end position for our line. So we can just create a vector line start, comma, line end, semicolon. And now we have a vector to hold the line start position and the line end position. Now we can apply and accept and just create our spare parameters. So go over to the right over here, create spare parameters for each unique call of ch, and we can just add lines like this. Right, so I'm going to set it to 2 lines and bring this back up, Alt plus E. So obviously our code doesn't do anything yet. It just creates some variables, they're just initialized, and we haven't really done anything with it yet. So next, we're going to create a for loop, because what we need to do is we need to say for each of these lines, add some points, right? So we say for int I equals 0. Remember the anatomy of the for loop. It's this int I equals 0. Then you have your conditional, as long as I is less than the number of lines, semicolon, then increase I. So what it'll do is create this I variable, which will be 0. As long as I is less than the number of lines, run this code. Once you're finished running this code, increase I by 1. Right? So that's pretty cool. It'll run our code, increase I by 1. If this is still true, it'll run it again. So in here, I'm going to make a float called theta. Now, theta is just a placeholder. You can call it whatever you want, right? I'm calling it theta because it's a math convention, but you can call it float pancakes if you want. Now, this is going to be the value that allows us to check where on our circle we currently are. So say we have the circle and we want to cut it up with 3 lines. How would we go about doing that? Well, we know a few things. We know that our lines equals 3. We know that the circle is made up of 360 degrees. And we want to know where to put our points so that we can create our lines. So now, remember that lines are made up of 2 points. So we only have to calculate half of the circle and then mirror it over, right? So we actually don't need 360 degrees, we need half of that. We need 180. So then the maths looks like this. 180 divided by the number of lines, which is 3, equals, and in this case, it's equal to 60. 60, 120, 180, 60. We now know what the distance between our points should be. So this one should be over here, and then we need to rotate 60 degrees around our imaginary circle. And we need to put a point over there, and then 60 degrees around our imaginary circle, put a point over there. Then we just need to flip it. So we need to put 1 over here, 1 over here, and 1 over here. And then we can just connect them up. So we connect these two, we connect these two, and we connect these two. Now, okay, it's not perfect, but these are now 60-degree segments. 60, 60, 60, and so on, right? So to figure out where we need to put our point is quite easy. We need to say the current line. So this first one will be line number 0. This one will be line number 1. This will be line number 2. Remember, it's only 3 lines. And so you can actually think of this as I. I equals 0. I equals 1. I equals 2. Then all you have to do is multiply it by this value. So the equation for theta, in our case, becomes the following. It becomes 180 divided by 3, or the number of lines. So let's rather do that, right? 180 divided by lines times I. That gives us theta. So theta equals. And that's just the mathematics symbol for theta. So now we know how we're going to position our points. And to get the opposite point, it's really simple. You just multiply it by -1 and you get the opposite point. And that would just be because of the way quadrants work. You know, this is something that you'll probably understand just from working in 3D. But if this is your Cartesian plane, you know, x and y, so if this is x and this is y, then this is your positive x-axis, positive y. This is positive x, negative y. This is negative x, negative y. This is negative x, positive y. So to get the diagonal quadrant, all you have to do is multiply any quadrant by -1. So multiplying this by -1 gives you negative x, positive y, which is this over here. Multiplying this up here by -1 gives you -x minus y. So that would be this one over here. And so we can do that exact thing. You know, this, whatever this point's position is, we can say times -1, and it'll give us the opposite point, right? That over there. And we could say times -1, it'll give us the opposite over there, times -1, it'll give us the opposite over here. So this might look confusing, but when we do it in Houdini, it might make a lot more sense. Okay, so now we know that theta should equal to 180 divided by the number of lines that we have times I, right? So now we know the distance between each of the points that we need to place. But that's degrees. How do we get this into a position? Well, we can use sine and cosine. And I'm not going to go into this too much, but you can look at a sine and cosine graph, and basically, if you feed in a certain number of degrees, it will return a value between -1 and 1. So all we have to do is we need to feed in our theta into a sine and cosine graph. And so we'll do x equals sine of theta, and y equals cosine of theta. And then all we have to do is say that line start is equal to set. And the reason we use the set instead of something like this, where we go x, y, 0, is because this is when you know that your values are constant. It doesn't work with variables. In this case, it'll throw an error. If we apply, you can see over here, it throws an error, right? It says unexpected identifier. And that basically just means that you can't use this type of syntax when you're working with variables. So you have to say set x comma y comma 0. So set is just a function that can handle variables. Apply, and in the next line, all we have to do is to add point. So we say add a point at this position. So geometry stream 0, and at position line start. So if we apply and accept, this isn't going to work, and I'll tell you why shortly. But if we check over here, and you may need to rotate around to see where your points are, but you can see that there's a point over there at where we would expect it, because it would draw a line straight down and cut the circle in half, but there's one over here. And this isn't right. It should be over there. It should cut this way and this way, right? These are the start points of our two lines. So let's press Alt plus E to bring this back up. And the reason it's doing this is because we are not working with radians. We are working with degrees. Now, radians versus degrees is just a unit of measurement. It's like centimeters versus inches, or meters versus feet. Right? It's the same thing. It's two different ways of doing the same measurement. So what's happening here is sine is looking for theta, but it expects it in radians and we're giving it in degrees. So all we have to do over here is just wrap this theta in radians. You can also wrap the line above in radians. We just say radians like that. And what that will do is it'll convert this theta value using this function called radians, and then sine can use that. And of course, alternatively, if you don't want to do it like that, you can very easily do it like this, where you wrap this entire line over here like that, radians. Now we have the two start points of our lines. And if you remember from earlier, we just said that the easiest way to get the opposite position is to multiply it by -1. So now that we've used x and y, it's very easy for us to write over x and y because we've already added our point and we've already assigned these values to line start. So we don't actually need x and y anymore, so we can reuse them. And that's the cool thing about variables. We can give them new values. You could say x equals -1 times sine of theta, right? That'll give you the inverse. But we know that x is already equal to sine of theta. So we can just multiply x by -1. And there's another way of doing that. You can say x times -1. Or the easiest way to do it is just to say x times equals -1. What it's doing is it's saying take x, multiply it by -1, and return the value of that into x. It's the same as saying x times -1 over here. So then we're going to do the same thing for y. Y times equals -1, and then we can say line end equals set x comma y comma 0. So these are our new x and y values, right? We've done this over here where we've used x and y, and then we used line start and add point. So after that, x and y can be used for something else. And so we just reassign some values to them and use it for our line end over here. Then once again, we could just add a point, 0 comma line end. Apply and accept, and there we have it. We have a point over there, and then the opposite points are added. The cool thing is, if we increase our lines, this works perfectly. So no matter how many lines you want, it'll always work. Alt plus E to bring this back up. Now we want to actually add these points together to create a line. Now, how do we do that? Well, there is a function called add prim. Much like add point, you can have add prim. Add prim is a bit different. So it takes a geohandle, 0, but then it also takes the type of primitive that you want. So you could have like a closed polygon, but in our case, we want a line, and that's called a polyline. Once again, you can actually check this out in the documentation if you'd like. You can even click on add prim and press F1, and there you can see it. It says geohandle and then the type, and it requires points, but we'll get back to that shortly. You can see over here it says poly, polyline, tet, sphere, circle, all of these things, right? So we want a polyline, an open polygon. Now you'll see that it also requires 2 points. It requires this PT0 and PT1. And what it'll do is it'll connect these 2 points up. Now, we have no way of calling this point and this point. right? There's no ways we can call them because we don't have them saved as a variable. We don't have their point numbers or anything like that. So what we need to do is we need to actually assign them to an integer. And this is something that's cool about the add point function, is that it can be assigned to an integer. So what we do here is we say int pt0 equals, and down here we can say int pt1 equals. Now what it will do is it will assign this point number to pt0 and this point number to pt1, and then we can use them over here. We can say pt0, pt1, and then apply and accept, and now we have it connected as a line. So I'd suggest saving from here, and we're just going to look at this code quickly and go through a couple of things. So what we're saying is, let's create a line variable. We can control how many lines we want. Create x and y that is equal to 0 to start with. Create two vectors called line start and line end that we can use later. So all of this is just initializing for what we're going to do later. Then in our for loop, we say create an integer called I, which is equal to 0 to begin with. As long as I is less than this lines variable, run this code over here. Once you've run the code, increase I by 1, and then check if this is still true. If it is still true, run it again. If it's not true, stop running it. In here, we calculate theta. Theta is equal to half of our circle divided by the lines multiplied by I. If it still confuses you, I'd recommend watching that back where I explained the whole circle thing. But then we convert it to radians because Houdini is happiest with radians and we've been using degrees. So we take that theta value that is now in radians, and then we use it to calculate our x and y. So we use sine of theta to calculate our x. And this will return a value between -1 and 1 based on a sine curve. This will return a value between -1 and 1 based on a cosine curve using theta. We then assign x and y to line start, right? So we set line start to be equal to x, y, 0. And we're saying 0 because this is flat, it's two-dimensional at the moment. We're not using the z component. We then say add a point from geometry stream 0 at the position line start. So we're taking this line start position and we're adding a point there. We also tell it to track this point number in an integer called pt0. We then invert our x and we invert our y to get the opposite positions and assign that to line end, right? So these new x and y values are assigned to line end. Then we make a new point. So we add another point at line end and we assign this one to pt1, point 1. Then in add prim over here, we add a polyline which connects point 0 and point 1. And the cool thing about add prim is that it also can track the prim number if you do something like int prim, right? You can make it int prim equals whatever. So with that, we have this nice little bit of code that just generates some lines for us that are evenly distributed. And you can actually see that they fit perfectly into a circle. If you create a circle and put it onto the XY plane, you can see that our lines fit perfectly inside of this circle. Now, our code has one issue that I want to bring up, and this is something that throws a lot of people off. It confuses a lot of people because it's one of those things that's very easy to miss, and it's something that you have to be coding for a little while to actually pick up on. You'll notice that when we increase this to a very high number, we have these open areas over here. All right, so something in our code is breaking. What's breaking is this over here, where we're saying radians, 180 divided by lines times I. We're saying 180 divided by lines, but the issue is this 180 is an integer, right? We're dividing an integer by lines, and we're not returning the decimal value. So when our lines value gets quite big, we end up with a small decimal point, and this code breaks apart. So what we have to do is we have to actually say 180.0. That just tells Houdini, hey, look, I don't want this to be an integer. I want this to be a float, because we told it to be a float over here. But when we're actually doing the calculations, we were using an integer. So it uses an integer. So we say 0.0, apply and accept, and it'll get those nice little decimal values. So now our code doesn't break apart. So that's just something that I wanted to bring up, because a lot of people might not understand why that happens. And this isn't a VEX thing. don't think like, oh my gosh, VEX is so silly, it can't figure out that this is supposed to be a float. This happens in a lot of coding languages where you have to say, okay, 0.0, this is a float. Treat it as a float. So when it does these calculations, it doesn't treat it as an integer. Right, so that's it for this part. That was quite a lot to get through. Hopefully you understood this all. If not, then I'd recommend watching that number file video that I suggested and maybe doing a quick read on sine and cosine. Right, I imagine that the only thing that would really be confusing in any way is probably this over here, this float theta with the sine and cosine, but really it's maybe a 5-minute read if you just want to learn about sine and cosine. So I'll see you next time where we will be adding the points to this. They'll be moving back and forth on a single line in simple harmonic motion, so they'll never touch, and it will create what looks like a circle. So until next time, bye.